Energy production and utilization are among the major concerns of today's society. The Institute of Thermal Engineering is a subsection of the Swiss Federal Institute of Technology, Lausanne, EPFL, where top research is performed in this domain. It is part of the Mechanical Engineering Department, one of the 12 departments of the EPFL, an institution located at the feet of the Alps by Lake Geneva. The department is divided into 4 institutes, of which this video presents the Institute of Thermal Engineering, IT. It is composed of 3 laboratories. The Laboratory of Industrial Energy Systems, LENI, the Laboratory of Heat and Mass Transfer, LTCM, and the Laboratory of Applied Thermodynamics and Turbomachinery, LTT. Based on its long experience in turbomachinery, the LTT provides a structured education for the students. This includes basic theory, as well as advanced subjects like transonic flows and unsteady phenomena in turbo engines. The main research interests of the LTT are focused on the compressor and the turbine of both industrial turbo engines and jet engines. First, we want to have a look at some research topics concerning the compressor.
Here you see a blade mounted in a Laval nozzle that allows research to be done on subsonic, transonic, and supersonic flows. Currently, pressure-sensitive paint measurements are carried out that allow us to directly record the pressure distribution on the blade surface. Here we have an example of the PSP method, where you can clearly see a shock in passing from supersonic to subsonic flow.
One important research topic is the sucking in of the boundary layer through a small slit. This prevents its separation from the blade surface and allows higher compression ratios and lower losses. This simulation shows the unsteady behavior of the shock boundary layer interaction. And here we see the same flow, but the boundary layer is sucked in. This installation is used to study the effects of vibration of a compressor rotor blade and the back pressure variations generated by a gust generator simulating the stator. Particle image velocimetry, or PIV, is used to obtain the velocity distribution of the flow. The zone of interest is illuminated by a plain laser light sheet. Here we visualize this zone with smoke. This visualization shows a shock that travels periodically on the rotor blade due to the back pressure interaction of the simulated stator. Many of the compressor blades that are used in research are manufactured in the department's own machining studio. Modern CNC machines are used to ensure a high-quality product. Now we present some of the research projects concerning the turbine.
We are here in the linear test facility of the Laboratory for Applied Thermics and Turbomachinery. In this test facility, we perform heat transfer measurements on turbine blade models. Therefore, we use the unsteady liquid crystal technique. We study the phenomena of film cooling with this method.
A shaped hole configuration to form a layer of cool air is tested. The model is covered with liquid crystals and is rapidly introduced in the hot air stream. In that way, a colour distribution will form representing the temperature. The interest of this research topic is to allow higher temperatures at the turbine inlet without overheating the turbine blades. This leads to a better overall efficiency of the engine.
This is the non-rotating annular test facility of the LTT. It is unique in the world and it is used for studying unsteady aerodynamics in turbomachinery in collaboration with industrial and academic partners.
The installation simulates one turbine stage with a rotor and a simplified stator. The rotor blades can be excited to vibration in order to study the effect on the flow. In contrast with conventional test facilities, the rotor is kept fixed and the flow is swirled instead. This simplifies greatly the transmission of unsteady measurements on the rotor. Here we see a schematic plot of the test facility. The airflow is disturbed by the simplified stator in order to simulate its effect on the rotor. The Laboratory of Heat and Mass Transfer is the newest laboratory of the Thermal Institute.
Our main field of research is two-phase heat and mass transfer, more commonly known as condensation and evaporation. SUSE Friatherm is interested in our work on falling film evaporation, falling film condensation, for the development of more compact heat exchangers for refrigeration systems.
The experiment recreates what happens in a falling film heat exchanger. The liquid is pumped and then distributed at the top. It flows then from tube to tube on the outside. The goal is to study the flow behavior between the tubes. Depending on the flow rate, three main different modes can occur. The first one at low flow rate is the droplet mode. When we increase the mass flow, the frequency of droplet formation increases and they form a continuous jet. We reach the column mode. Increasing the flow rate further, the columns merge to form a continuous film. This mode is called a sheet mode. The goal is to develop a prediction method for the flow transition and create a flow map. This map will be used in the heat transfer model in the future. With a high-speed camera, we can see in detail the physics of the creation, evolution and impingement of a droplet. The arrival of the droplet on the tube is important for heat transfer. The liquid at this point is accelerated. That improves the heat transfer significantly. Being able to visualize this phenomena in slow motion helps the research team to understand it.
Void fraction is a very important parameter in the study of two-phase flows. You can think of void fraction as the cross-sectional porosity of the gas phase in the two-phase fluid flowing through a channel. In our laboratory, we've developed a new system for taking laser sheet assisted videos of two-phase flows in order to measure void fraction. And what you can see here are some of these videos which are treated for our image processing.
The installation allows for the calibration of the method before using it on the boiling flow test facility, where a new void fraction model has to be developed. A camera permits the taking of pictures of interfacial flow structures. Controlling the flow rate, different flow regimes can be established. Laser light illuminates the cross-sectional area. The area which corresponds to the liquid has much higher light intensity. This effect will be used afterwards to determine the interface between the gas and the liquid. Because of the optical deformation from refraction through the tube wall, the images have to be post-processed. A picture of a grid placed in the measured tube is taken in normal light. Based on the initial shape of the grid, a computer transformation of all the images can be performed. Finally, the pictures are processed. The result is the area of void fraction represented by white pixels.
For the future, we are interested in the cooling of electronics chips, development of micro refrigeration systems, modeling of micro reactors, and the development of two-phase cooling of large engines and motors for more efficient operation and the reduction of pollution.
The Laboratory of Industrial Energy Systems deals with questions of optimization of energy utilization for sustainable development. One of its research interests is internal combustion engines. Using detailed simulations of the flow in a cylinder, fuel injection is studied and optimized. The aim of this project is to improve the efficiency of this industrial cogeneration motor. It is a pressure ignition motor burning natural gas. The principle of cogeneration is to reuse the unavoidable heat loss of the motor. The cooling fluids are retrieved in order to feed other processes, such as different industrial and domestic heating systems or a Rankine cycle. Another project involves research on a solar power plant. The principle of this plant is to use solar energy to run 2 successive Rankine cycles, that is 2 turbines coupled with electric generators. If the solar radiation available is insufficient, the heat of a cogeneration motor is used to supplement it.
These adjusted mirrors focus the solar radiation on this collector tube, in which pressurized water is used to transport the heat. Then the water from the collectors is used in this heat exchanger to vaporize the fluid of the Rankine cycle that will run this turbine.
A more recent research project is the one on fuel cells.
The fuel cell consists, just like a classical battery, of 3 layers: an ionic conductor between 2 catalyzers, the anode in green and the cathode in black. They effect a charge separation from chemical components. That charge is retrieved in the form of usable electric current. Gaseous fuel, hydrogen or natural gas, is introduced to the anode and air to the cathode.
A crucial problem for sustainable development is to optimally integrate these technologies in complex processes. At the LENI, genetic optimization algorithms are used for such studies. The principle of this technique is to characterize every possible solution to the problem by a genome from which an evaluation function can be computed. By reproducing, crossing over, and mutating a number of arbitrarily generated initial solutions, convergence is possible to solutions with maximal evaluation functions. In that way, complex industrial processes can be optimized, such as here the plant for distance heating in Lausanne. The heat from the waste incinerating plant, burned sewage treatment gases, rubbish wood combustion and gas turbines with their specific yearly power distribution have to be optimally used to cover the customer's needs. For the university buildings, EPFL has its own thermal plant on a smaller scale. Located right behind the university, it is an excellent opportunity to demonstrate to the students the applications of the taught theory. The global character of today's energy issues needs a global solution strategy. The LENI works in a close collaboration with MIT and the University of Tokyo. An important tool is this internet-based application called DOME.
Voilà, donc on s'appuie sur un système d'information géographique qui donne la
This part of DOME is a database of geographical information containing the distribution of different types of buildings in the city of Tokyo. I can select the zone and the type of buildings that I'm interested in, and DOME returns the total surface and distribution of these buildings. And that way, we optimize the energy production distribution using thermoeconomic models of the 3 universities that are accessible through DOME.
modèles thermoéconomiques qui ont été développés dans les 3 universités.
The collaboration of the 3 universities is coordinated by the Alliance of Global Sustainability, AGS, that regularly organizes conferences on current topics. Through this research, the Institute of Thermal Engineering has provided a substantial contribution to the development of industrial know-how and continues its efforts towards discovering more efficient uses of energy and finding renewable and environmentally safe energy resources.